Welcome, folks. Today, we are discussing the groundbreaking paper, BERT, Pre-Training of Deep Bidirectional Transformers for Language Understanding.
I've heard a lot about BERT, but I'm not entirely sure what makes it so special. Can you give me a quick overview?
Sure. BERT, which stands for Bidirectional Encoder Representations from Transformers, is a language representation model. What sets it apart is its deep bidirectional approach. Unlike previous models that process text either left to right or right to left, or shallow concatenation of both, BERT processes the entire context simultaneously in all layers. This allows it to capture much richer contextual information.
That sounds significant. How does this bidirectional approach impact its performance?
It leads to state-of-the-art results on a wide range of natural language processing tasks. The paper reports improvements across 11 tasks, including question answering and language inference. For example, it pushed the GLU score to 80.5%, a 7.7% absolute improvement over the previous best. Similar significant gains were seen on other benchmarks like multi-NLI and Squad.
Wow, those are impressive numbers. But how does BERT actually achieve this? What's the underlying mechanism?
The key is its two-stage process, pre-training and fine-tuning. During pre-training, BERT is trained on a massive amount of unlabeled text using two unsupervised tasks: a masked language model, MLM, and next sentence prediction, NSP. The MLM randomly masks words in the input and trains the model to predict them based on the context. NSP trains the model to predict whether two sentences are consecutive in the original text.
So the MLM is what gives it the bidirectional capability?
Exactly. By masking words and requiring the model to predict them based on the surrounding context, the MLM forces the model to consider both left and right context simultaneously. This is unlike traditional language models, which only consider one direction.
And the NSP task helps with understanding sentence relationships?
Precisely. It helps the model learn to understand the relationships between sentences, which is crucial for tasks like question answering and natural language inference. After pre-training, the model is fine-tuned on specific downstream tasks with minimal task-specific architecture modifications, usually just adding an output layer.
The paper mentions two model sizes, BERT base and BERT large. What's the difference?
BERT base has 12 layers, 768 hidden units, and 12 attention heads, totaling 110 million parameters. BERT large is significantly larger, with 24 layers, 1024 hidden units, 16 attention heads, and 340 million parameters. Unsurprisingly, BERT large generally outperforms BERT base, especially on tasks with limited training data.
It seems like the size of the model is a significant factor in its success. But is the size alone responsible for the improvements, or are the pre-training tasks equally important?
That's a great question, and the authors address this with ablation studies. They found that both the bidirectional nature of the model, enabled by the MLM, and the NSP task are crucial for achieving state-of-the-art performance. Removing either significantly degrades the results. The bidirectional nature is particularly important for tasks requiring understanding of both preceding and succeeding context.
So, BERT's success isn't just about throwing more parameters at the problem. It's about the clever design of the pre-training tasks and the bidirectional architecture?
Precisely. The paper highlights that the deep bidirectional nature, combined with the effective pre-training tasks, allows BERT to learn rich contextual representations that generalize well to various downstream tasks. It's a powerful combination of architecture and training methodology.
The paper also discusses different approaches to integrating BERT into downstream tasks, right? Fine-tuning and feature-based approaches?
Yes, the paper explores both. The fine-tuning approach, where all parameters are fine-tuned on the downstream task, generally yields better results. However, the feature-based approach, where pre-trained representations are used as features for a task-specific model, offers computational advantages and can still achieve competitive performance.
This is fascinating. It seems BERT has significantly advanced the field of NLP. What are some of the key takeaways from this research?
The key takeaways are the demonstration of the power of deep bidirectional representations, the effectiveness of the masked language model, and next sentence prediction tasks for pre-training, and the versatility of BERT in adapting to various downstream tasks through both fine-tuning and feature-based approaches. It's a significant contribution that has spurred a lot of further research in the field.
This has been incredibly insightful. Thank you for explaining this complex paper so clearly.
You're welcome.